Hello, my name is Frederico Henrique Ferreira, and I've been working with my advisor, Dr. Luis Antonio, and a collaborator, Dr. Yahya, in this project entitled Zinc-2 Glycine Complexes and Early Analysis through a Theoretical DFT Approach. It is well known many ions take place in the bloodstream, either naturally or due to long exposures to unhealthy situations. Those metallic ions could eventually interact to some free amino acids and make complexes not yet deeply studied by researchers. Many papers were released about complex monomers, the ones with just one metallic center, but only few widens the discussion to dimers and tetramers. The scope of this project is to propose complex structures, beginning with glycine and zinc-2, and analyze those complexes in terms of its electronic and structural properties. Hereafter, it is expected to make comparisons with some synthesized reported complexes and widen the focus to other ions and ligands. Glycine is the simplest amino acid in structure, and glycylglycine is its dimer. The metallic center chosen was zinc-2. The systems were optimized according to the DFT functional and basis set shown. There were also performed both a frequency and a population calculation. All jobs were carried with the software package Gaussian 09, and electronic properties were evaluated through AOMix software. The optimization resulted the following structures for the complexes: from left to right, zinc with 1 glycine, zinc with 1 glycylglycine, zinc with 2 glycines, and zinc with 3 glycines. Here, there has been proposed 3 structures: an octahedral zinc-glycine complex, a dimer, and a tetramer. The distances between the metallic center and both the oxygen and nitrogen are reported in this screen. Nitrogens are the ones with the shortest distances in average. Among the oxygens, the ones from water molecules have shorter distances than the ones from glycine. When comparing the angles, values fluctuation were very low, and the mean reported was 72.3 degrees. The NBO analysis shows there are high stabilization on the system due to ligand-ion electronic donations. Zinc-nitrogen bonds results the highest stabilization when compared to the zinc-oxygen bonds. This is assured by the shorter nitrogen-zinc bond distance. Here are some NBO illustrations. Orbitals overlap that causes the stabilization energies are shown for zinc-glycine, zinc-glycylglycine, and zinc with 2 glycines, as well as for zinc with 3 glycine ligands. Coming back to our table, NBOs for the other 3 proposed complexes were also evaluated, and here is an example of the zinc-glycine NBOs overlapping, as well as for zinc-oxygen orbitals. HOMO and LUMO molecular orbitals were also plotted. Here there is an illustration of the dimer. Energy gap varies from 10.469 electron volts for the glycylglycine complex to 11.33 electron volts for both octagonal and the dimer structures. Our conclusion was that the geometries proposed show the stability, the interaction energy does not get lower with more glycine ligands. Besides the dimer and the tetramer, energy values are quite identical. The energy gap between the frontier molecular orbitals fluctuate about 1 electron volt, and all results were concise to each other and demonstrates the stability of those complexes. I would like to thank both NEQC and the Federal University of Juiz de Fora for the resources they granted me, and CNPq for my scholarship. Thank you very much indeed.